Today we continue discussing vectors, but I would like to remind you what we can do so far. So if we have vectors v and w and a scalar c, what can we do so far? We can add. This is vector addition. We discussed vector addition not only component-wise, this was the algebraic viewpoint, but also in terms of arrows. We had triangle rule and parallelogram rule. We can subtract v minus w. This is subtraction. And we can also take cv. This is scalar multiplication. But you notice nowhere have I said anything about multiplying vectors v and w. And so this leads to a very natural next question. What about a vector product? Some say v times w. Well, the short answer is we cannot multiply vectors. But I do have a longer answer than that. Instead, we actually have two products. We have two products, but they're very different. And both of them we will discuss in the coming sections. The first one is called the dot product, and this is the focus of today. Dot product is much more general. What we need is v and w. They are just vectors in Rn. Okay, they need to be the same length. They're sitting side the same Rn, but it can be in any Rn. The other one we will discuss is cross product, and this is different, is very specific. V and W must both be in R3. There's not a cross product in R4 or in R2 or something like this. V and W are both in R3. Now, that's just one difference. Another important difference, this is the dot product. It's written like this, but V dot W, this is a scalar. Whereas V cross W, the cross product is a vector, and it's a vector in R3. Okay, so this highlights some of the differences. Generally, like I said, you cannot multiply two vectors. We have these two products, and the one we will discuss today is here, and this produces a scalar. This is an important thing to keep in mind as we compute dot products. Now, let's move into the definition of the dot product, and then we will do some examples and say some other things. In vectors, there's always two viewpoints. There's an algebraic viewpoint that's thinking about vectors really in standard position, thinking about components and working with components. Then there's a geometric viewpoint, and that's thinking about arrows and angles and lengths. So let me tell you the dot product in each one of these. Here, V is here, V1 through Vn, and W is W1 through Wn. The dot product, we take V1 times W1 and add V2 times W2, and then all the way out to Vn times Wn. We can write this in summation notation. It's a sum, k equals 1 to n of V k W k. So you take and multiply the corresponding entries in each component and then add all of this up. This is the algebraic viewpoint of the dot product. Now, the geometric is as follows. If you have V and W both in Rn, this would be the length of V times the length of W times the cosine of theta, where theta, this is between 0 and pi, and this is the angle between the two vectors, V and W. We can always take theta to be between 0 and pi. For example, say here is V and here is W. Okay, here's two vectors. You would not measure theta to be this angle. That would be not between 0 and pi. Instead, this one would be theta, right? And if they happen to be parallel and pointing in opposite directions, in this case, well, here is theta, oh, here. And this would be pi, for example. Okay, so you can always do this. Given any two vectors in Rn, you can measure the angle between as being, or here, between 0 and pi. Okay, this is the angle between two vectors. And the dot product can be calculated geometrically like this. Now, we may use the dot product to find the angle between two non-zero vectors v and w. So what did we just write down? We just wrote down that v dot w is length of v, length of w times cosine theta, okay? If v and w are non-zero, then so are their lengths, and I can just divide by the lengths. I get cosine theta is v dot w divided by the length of v times length of w. Okay, so this gives us a value of a cosine. How would we find the angle? Well, you just use cosine inverse. So we get theta is cosine inverse of v dot w divided by the length of v times length of w. This might be the first time we talked about cosine inverse in Calculus 2, but you might remember this feeds in a value of cosine, and it gives you back an angle between 0 and pi. This is the way cosine inverse works. So you will always, let me draw a unit circle. It always gives you back an angle up here between 0 and pi. Cosine inverse does. And that's exactly what we want for the angle between two vectors. What I'd like to do now is I would like to discuss the concepts of acute, obtuse, and right angle for the angle between two vectors and understand how these are related to the dot product, okay? Now, first of all, what is an acute angle? Theta is acute, means that 0 is less than or equal to theta is strictly less than pi over 2. It means theta sits, well, in here, but not including pi over 2, okay? Now, what do you notice if we think about cosine? This is precisely when the cosine is positive. Now, here comes the dot product because we have the cosine right here. V dot w over length of v times length of w. You notice the denominator is the product of two lengths. They're both non-negative. The denominator is non-negative. So the sign, and I mean SIGN, the sign of the cosine of theta comes from here, okay? So here, cosine theta is positive. This happens if and only if v dot w is positive. And this is the characterization I was talking about. Now we know precisely the angle between v and w is acute precisely when v dot w is a positive number. Now, let's do obtuse next. Well, obtuse in the picture does not include here. It's here, and all of here is where theta will be. And this says that pi over 2 is less than theta is less than or equal to pi. Now, we translate this into a statement about the cosine. This says cosine theta is negative. Well, just like my discussion before, this is the cosine. The denominator is positive, so the cosine is negative provided the numerator is negative. And so we get v dot w is negative. So this is the characterization for when the angle between v and w is obtuse. We take v dot w, and if we get a negative number, we know that the angle between those two vectors is obtuse. Now, the only thing left is a right angle. This would say theta is pi over 2. And this happens precisely when the cosine is 0. And if you look here, When is the cosine 0? Well, it's precisely when v dot w is 0. So this is the characterization of having a right angle. Now this is so important, it has a bunch of words. The two vectors are called perpendicular or orthogonal, or you might even see the word normal. This is another word and they all mean the exact same thing. Perpendicular, orthogonal, normal, they all mean, this is the definition, it just means that v dot w equals 0. And don't put a hat because it's not a vector, v dot w is a scalar. And great, okay, this is the characterization. So now let's do some examples. I left off part of this. Is the angle between B and W acute, right, or obtuse? And then is the angle between, I should have the same thing listed here. Now let's read the question. We're given two vectors in our 3. We want to figure out if the angle between them is acute, right, or obtuse. Then we will find the angle. And if we have some nice cosine value that we know the theta for, that's fine. If not, we can just leave cosine inverse in our answer. You'll see this in the homework exercises as well. So let us first calculate the dot product. This would be 1 times 1 plus 2 times 0 plus 3 times minus 1, right? We have 1 minus 3, which is negative 2. Now, before I even calculate the value of the angle between the two vectors, immediately I know the answer to the first question. This is negative, so I know that theta is obtuse because the cosine is negative. Now, the other pieces of information I need the length of v, I need the length of w, and these are both square roots and square roots. So here, length of v is 1 squared plus 2 squared plus 3 squared. This is a square root. We have 1 plus 4 plus 9. This is square root of 14. This is length of v. And then for length of w, we have 1 squared plus 0 squared plus minus 1 squared. This is the square root of 2. Now I have everything I need to get theta. I know that theta is the cosine inverse of, well, you take v dot w divided by the length of v times length of w. And this is 14 and here. This is theta. You could calculate this in your calculator if you wanted to. In fact, in this example, I can slightly simplify. I can write this as cosine inverse of, well, the denominator, if I multiply those two square roots, I get the square root of 28, which is 2 times the square root of 7. So I have a square root of 7 in the denominator and a minus 1 in the numerator. But my first answer was fine as well. Okay, this is this answer. Now let's move on. We have another pair of vectors and we have the exact same question. We want to determine if the angle between them is acute, right, or obtuse, and find the angle. So first thing we do, just like in the last example, we compute a dot product. This gives us 3 times 0 plus we have 4 times 4 plus we have 0 times 5. In this case, we get 16. This is positive. And so, because the dot product is positive, this would say the cosine of the angle between them is positive, and this tells us theta is acute. Now, let's go about actually finding this angle. The length of v is a square root, and length of w, square root. Length of v is the square root of 3 squared plus 4 squared plus 0 squared. And this is the square root. We have 9 and 16. Okay, this is just 5. Then the length of W, we have 0 squared plus 4 squared plus 5 squared. This is a square root. (16) plus 25. This is the square root of 41. Okay. Now, theta is cosine inverse of, we take the dot product divided by, here, 5, the square root of 41. This would be theta. Just as a comment, this number, 16 over 5 times the square root of 41. If you do enter this in your calculator, let's see. This is approximately 0.4998. It's very close to a half. And so theta is approximately, this one we actually know. It's not equal because this is not 1/2, but it's very close. So theta is approximately, well, the cosine is 1/2 at, it's going to be up here, pi over 3. So theta is very close to pi over 3 here. It's not exact, but that was more a comment than anything else. We can leave the cosine inverse in our answer here. Now, I want to make a few comments about the dot product and parallel vectors and dotting a vector with itself. So let's go back and remember, what does it mean to be parallel? Two vectors are parallel provided they are scalar multiples of each other. That's for non-zero vectors. Okay, so for example, you either have this picture where this is V and this is W. In this case, they point in opposite directions and the multiple is a negative number. So V will be a negative number times W, and similarly, W will be a negative number times V. That's one possibility. The other possibility is V is like this, and W points in the same direction. So this one is also parallel. Okay? Now, what does this say about the angle? Well, you see theta is either 0, that's in this case when they point in the same direction, or the theta is pi, and that's this case when they point in opposite directions. Let's keep going with this unraveling what this is going to say about the dot product. In particular, we see cosine theta is either 1 or -1. Okay? So when you have two parallel vectors, so V, W, parallel, we will have that V dot W will be plus or minus length of V times length of W. This is kind of an interesting observation when you have parallel vectors. Okay, now my other observation is about dotting a vector with itself. Dotting a vector with itself, we are in this situation. V and V, definitely they're parallel. The angle between V and itself is 0. And so we get, this is length of V times length of V times 1, or the length of V squared. You could also see this using the algebraic viewpoint of the dot product. And so this is my second observation. It's here that when you dot a vector to itself, you get its length squared. Okay. Now, here are two examples where we'll determine if these pairs of vectors are parallel, perpendicular, or neither. So what we can do, parallel, you can try to see, is one vector a scalar multiple of the other? Perpendicular, take their dot product. Do you get 0, right? Here, let's do the first one. So I'll just start and just take the dot product. We get 6 times 2 plus minus 2 times 5, and then plus minus 1 times 2. This is 12 minus 10 minus 2. This is 0. We see these are perpendicular, okay? The angle between the two is right. B, W are perpendicular. Just also as a comment, they're not parallel because we would need one to be a multiple of the other. And here, this is a 6, this is a 2. That would say that V needs to be 3 times W. But then you look at the second entry, and V is 3 times W does not work for that entry. So you see they're not parallel. We could also see they're not parallel because this, for example, does not hold. But we have determined the answer already. V and W are perpendicular. Now, let's move on to the next example. These I have written as linear combinations of the coordinate vectors I and j, and this is perfectly fine. The first thing I'll do, just like in the last, let's take the dot product, V dot W, and see if it's 0. If we take, this would be 2 times minus a half plus minus 1 times a fourth. This is minus 1 minus a fourth. This is negative 5/4. This is not perpendicular. In fact, because the dot product, this is a comment and an important one, because the dot product is negative, we know the angle between these two vectors is obtuse. Okay? Now, the other thing we need to check is parallel. In fact, V and W are parallel. And how are we going to see this? Well, let's just notice, if we take W and multiply by minus 4, what do we get? We get minus 4 minus 1/2 I plus 1/4 J. And this is, let's multiply all this through, this is 2I minus J. This is V. Okay, so we found the relationship that you take minus 4W and you get V, or equivalently, you could take minus 1/4 V and you get W. And this says these vectors are parallel. This is the answer here. Okay. Next, let's consider the vectors I, which was 1, 0, 0, and J, which is 0, 1, 0, and K, which is 0, 0, 1. And I want to make some observations. Okay, what happens here? Take I dot K, or I dot J, or let's see, there's one more we missed, J dot K. Well, I dot K, for example, this would be 0 plus 0 plus 0. This is 0. And I dot J, we have 1 times 0 times 0 times 1, like this. And similarly, J dot K, we get 0 plus 0 plus 0. Okay? And there's more than that. These are all units. Okay, they're unit vectors. I think I mentioned that last time. So you notice we have this collection of vectors that are unit and they are pairwise orthogonal. So these are unit, pairwise orthogonal vectors. That is what the observation that we make in this example. Now, let's do one more example before I talk about some properties of the dot product. And it's here. I give you two vectors, V and W, but W has some constant here. And we want to find the constant C such that V and W are perpendicular. So what we need to do is take the dot product and set it equal to 0. And that will allow us to solve for constant C. Okay. V dot W is 2C And then plus, we have 4 times 5. And plus, this is minus 17 times 1. Okay, so we get 0 is 2c. Then we have 20 minus 17. This is plus 3. 2c will be minus 3. And we get the constant is minus 3 over 2. For this value of c, we would have v and w perpendicular. And it just uses that v and w are perpendicular provided their dot product is 0. Next, I'd like to talk about some properties of the dot product. In this course, I will just use them a little bit, but you'll use them a lot more in, say, a linear algebra course or something like this, which I recommend you take. Linear algebra is tons of fun. It's one of my favorite courses. Okay, so let's say u, v, and w are all in Rn. And let's say c is a scalar. Then I'm going to list some properties of the dot product. First of all, we can dot product in any order. Oh, should have w dot v like this. Now this makes sense. If you think algebraically, well, we would just have a sum of v1, say vk, wk. This would be a sum, k equals 1 to n. But you could certainly write it as wk, vk, right? And so that would tell us v dot w is w dot v. That's thinking algebraically. If you think geometrically, length of v, length of w, cosine theta, that would be v dot w, and you just interchange v, length of v and length of w, and you'd have w dot v. So this definitely holds. Okay, I was just talking about why it holds briefly, but this is one property of the dot product. Another one is if you take a constant times v dot w. You can write this a number of ways. You can either multiply c by the constant and then dot w, or you can multiply w by the constant and then dot v, and all three of these are equal to the exact same thing, which is you take the constant like this. Okay? All of these. Certainly this is equal to this. That's sort of definition. But then these two are also equal to that you can think about and check yourself if you're interested. The last property I'll mention is if you take, here's where I'm going to use the u, dot. How does a dot product distribute across a sum? And this is kind of neat. It works just like you would expect when you multiply a number times a sum of two numbers. In that, it's u dot v plus u dot w. And this you can also justify if you're interested. Maybe I'll just mention what it uses. It uses, if you have, say, ui, this would be in the ith component. This is exactly what I was saying, how a product distributes across a sum for numbers. This is ui, vi plus ui, wi. This is, well, this is really what's happening in each component of the dot product. So this is what this uses. Okay, so these are three properties which I mentioned in this course. I will just briefly use, but you might use them a lot more depending on the courses you take in the future. Now, let's do one example where we use these properties to calculate something, and then we'll move into the final thing I will discuss in this section, which is called orthogonal projection. So, here's what we're given. A and B are orthogonal vectors, and this word is an important part of the problem. And we're also told the length. The length of A is 2, the length of B is 1, and we want to find this dot product. Immediately, this is a dot product. We are looking for a number, okay? But because A and B are orthogonal, what does this mean? So this part, this says A dot B is 0. Equivalently, it says B dot A is 0. So if we take the dot product in either order, somehow expanding this, then we get 0. This is what we will use here. Now, what we want here is this dot product. We have A plus 2B dotted with A. So I can use, how do you distribute a dot product across a sum? Well, this would be A dot A plus, for the moment it's this, 2B dot A, right? Then we have A dot A plus, I can write this as 2B dot A, okay? I'm using the properties here. Well, A dot A, this is the length of A squared, and A and B are orthogonal, so B dot A is 0. Oh, well, the length of A squared is 2 squared. We have 4. So this is the answer here. In fact, we didn't even use the fact that B had length 1. We didn't use it in this calculation. Now, the final topic we'll talk about in this section is orthogonal projection. This is super important. This is super important just generally in life, okay? You will see this again in linear algebra, but it's just a very important concept. So, say I have some vector v here, and it needs to be non-zero. Okay, fine, mine certainly is. Now I have another vector f. I will draw f here. And what I want to define is the projection of f onto v. It has two different notations. You will see it written this way, v, f, you will see it written this way, f sub v. You are projecting onto v, okay? Now, what is it? I can draw in the picture, and from the picture and properties of the dot product, we can figure out the exact formula for the projection. Here's what I'm going to do. This will make a right angle, and then the projection will be here. So this is this f sub v, okay? Well, we see here that fv is a multiple of v. So let's write that. We want fv to be a multiple of v, okay? But not just any multiple, it's a special one, so that here, this makes 90-degree angle. So I will call this f sub n, this vector. Now, what is this vector? Well, if you take f, and then here I'm going to think triangle rule, and then subtract, oh, that's too much, f minus fv, right? This is f minus fv. That is here, oh, here, right? This is this vector. F sub n is f minus fv, right? That would be here, which is exactly this vector. So fn is f minus fv, and we want fn orthogonal to v, just like you see in the picture. Well, let us just set this, which is v dot fn, we will set this equal to 0. Okay, that will make it orthogonal. Then we will figure out what the constant c must be. Once we have it, that will give us a formula for orthogonal projection, and you can just use the formula for orthogonal projection. You don't have to go back through this every single time, but it's nice to know where the formulas come from because they really make sense geometrically. V dot Fn is V dot F minus Fv. Let's use the fact that Fv is CV. V dot F minus CV. Okay, now I will use the property of dot product. Well, I'm going to use a few properties that we discussed. This is V dot F minus, I can write this as C V dot V. I sort of use a few properties at once, but this is definitely the case. Now, you see, I almost have this. Given F, given V, can you compute C? Yes, you can. All I need to do is just solve for it here. We get that C, V dot V, equals V dot F. And now, let's just solve. C equals, I'll write it this way, F dot V, certainly I can, over V dot V. Okay, look how fantastic that is. Given F, given V, can you find the projection? Like I said, yes, we can. Here's the C. So the projection, I'll write this in black and put a box around it. F sub V, this is the projection. We take this constant, and multiply by V. Okay, this is the orthogonal projection. We will add some highlighter to this. This is what you can put stars on in your notes. This is the formula that we use. Now, there's a little bit more terminology here for FV and FN, and so I will just mention that, then we'll do an example. FN, this is FN. It is the component of F normal to V, and it's F minus FV, this projection, and the component of F parallel to V, this is this FV. This is, or you might see it, the projection onto V of the vector F, okay? So this is just some language that you might see in our text, also in future courses. Now, okay, great. Now we have a specific example. So let's do everything we just discussed. I can go back and copy this. Okay. This is the projection formula that we just really derived because we knew what we wanted FV to be. So let's do it here. We have a very specific example. This will help illustrate how we compute orthogonal projection in general. Okay, well, we need all of these quantities. We need F dot V and we need V dot V. F dot V, well, this is 2 times 1 plus 1 times 0 plus minus 1 times minus 2. This is 2 plus 2. F dot V is 4. Then we need V dot V. This is 1 times 1 plus 0 times 0 plus minus 2 times minus 2. This is 1 plus 4. This is 5. Okay, now we're ready for the projection. F sub V. Well, the coefficient, we take 4 over 5 and then multiply by V, 1, 0, minus 2. And we can write this as 4 over 5, 0, minus 8 over 5. Okay, this is the projection. Now we have a second part, calculate the projection. And you could also write this just as a comment, the projection, like this, okay, both ways. It's two different notation for the exact same thing. But there's another part here, which is to find the component of F normal to V. And that's just here. We take F with a difference of vectors. We take F minus the projection. So let's write that here, Fn. This is F, which is 2, 1, minus 1. And we subtract the projection, 4 over 5, 0, minus 8 over 5. 2 minus 4 over 5 is 10 minus 4 over 5, or 6/5. And then we have 1 minus 0, which is 1. Then we have minus 1 plus 8/5, which is 3/5. Okay? So this one is here, Fn. Now, we're done with the problem. We're finished, but it's not a bad idea to check. So let's check here. Check. We should get this normal component is perpendicular to V. This is really how we came up with this formula, if you remember. But it's always good to check in an actual exercise because you can see, for instance, if you made a algebra mistake, then we wouldn't get this dot product is 0. So here we go. Here, Fn is 6/5, 1 3/5, and we take the dot product with V, which is 1, 0, minus 2. Now we get 6/5. We have plus 0, and then we have minus 6/5, which is 0. And this is exactly what we wanted here, right? Fn and V are perpendicular, just as we would hope and as we should have. So this is all I have to say about the dot product and orthogonal projection. Thank you.